Good morning, everybody. Yet another Codeforces round, one day after the last one. Today we have an educational round, which hopefully means we'll learn something new. I am about 4 minutes late, 3 minutes and 20 seconds late, but I guess that's fine. You know, I'm not too worried. It's not rated for me, so it's not the end of the world. And it's only really a problem if I solve voice crack. Ooh, it's only really a problem if I solve a problem between the end of contest and 4.5 minutes after, right? So here we go. All right, problem A. Pizza Forces. Oh my goodness. Pizza Forces is Petia's favorite pizzeria. Pizza Forces makes and sells pizzas of 3 slices, small of 6, medium of 8, and large of 10. Baking them takes 15, 20, and 25 minutes respectively. So is small the most efficient per slice? I think possibly. And friends will come, so we decided to make an order up from his favorite pizza. He wants to order so much pizza that each of his friends gets at least 1 slice. The cooking time is the total baking time of all pizzas in order, or in the order. From the minimum number of minutes needed to make pizzas that contain at least n slices in total. Okay. So what is the LCM of each of these? We can divide each by 2. So then we have 3, 4, and 5. We can divide each of these by 5. Takes 3, 4, and 5. Yeah. So we can add 3, 4, or 5. And then the cost of that is 3, 4, or 5 times 5. Alright, so this is some chicken nugget theorem stuff. I don't know if you guys have seen Numberphile, but they have a chicken nugget theorem that they invented. Or maybe they didn't invent it, maybe they just presented on it. But the chicken nugget theorem is something to the effect of we can make every number as a sum of 3, 4, and 5 that's at least 3. So we can make every number exactly in particular. So we can do 3, 4, and 5, and then we can do 6, which is 3 plus 3. And then here we have a range of 3, right? So any other number we can make as 3 plus the previous. So really, this is a super easy problem. So if n, well, okay, so n equals n plus, so we want to divide these by 2. So n plus 1 over 2. And now we can do 3, 4, 5. Okay. So we have n. So if n is less than, I guess let's just say n equals math.max of n in 3. If it's less than 3, we can only make 3. And then at the end, sys out n times 5. And I think that's it. $30, $40, $7, $50, $15, a big number in this. All right, looks good. Let's submit problem A. So yeah, that's the idea behind A. It's chicken nugget theorem, and noticing that everything is basically the same cost. All right, we got it. Nice. 2 tables. We have 2 axis-aligned. Wait, you have an axis-aligned rectangular room with some width and some height. In the lower left corner is a point 0, 0, and the upper right corner is WH. There is a rectangular table standing in this room. The sides of the table are parallel to the walls, and the lower left corner is here. Upper right corner is here. We want to place another rectangular table in this room with this width and this height. The problem is sometimes there's not enough space to place the second table without intersecting the first one. You can't rotate any tables, but you can move the first table inside the room. Got it. So, wait, we can't rotate them, but we can move the first table? Oh, what's the minimum distance you should move the first table to free enough space for the second one? Is it guaranteed -1 if there's no way to do it? So you could place the first one above, below, or to the left, or to the right. Yeah. So I guess we just go to work implementing these because it's kind of ugly. I think that might be the only real way of doing it. So we're given the width and the height. I don't know if I mentioned this. Solutions will be at the end of the video. But yeah, kind of goes without saying at this point. Alright, so now we have x1, y1, x2, y2, and w and h. Okay. So in x1 equals this, x2 equals this. No, sorry, this is y1. And then y2 equals this. Alright, and then we're given int can w equals this, and then candidate height equals this. Alright, so these go from 0, right? Yeah, from 0 to that. Alright. So let's just call this W2 or width 2, and let's call this height 2. Okay. Yeah, so we can place it to the left. It's always going to be an integer. Yeah. Okay. So if ans equals integer dot max value, print -1, otherwise print ans. Okay, now we have to actually solve this. So if width 2 plus width 1 is less than or equal to the width, then there are two things we can do, and then if height 2 plus height 1 is less than or equal to height, a few things we can do here. These two things are, we can place to the left, or we can place to the right. So int new x2 will be width 2. So ants equals math.max of ants and what is this? So we need to move it to the right. Yeah, okay, and then at the end, ants equals math.max if ants was 0. So we need to move it to the right, which means it needs to be new x2 minus x1. It's new x1. Yeah, so we can move it to the right to this position. Okay, we can also place to the right. So what is this? So we have int new x2. This will be width minus width 2. And ants equals math dot max. And this should be math dot min. Math dot min as well. Ants or the new or x2 minus the new x2. Yeah, okay. So now this is a similar thing, so we can place above, or this is below, I guess, the way it's worked. Oh, are they guaranteed these are in the right order? They are, okay. So we place below, so int new x1 will be height 1. Ants equals math.min of ants, and then, so this will be new x1 minus, new y1 minus y1, should be a y, and then we have int new y2, this is placing above, new y2 would be height minus height 2. And then ants equals math.min of ants, or y2 minus new y2. Good, I think that's it. And then we print the answer. Let's see if they have this verified. No, not even close. Okay. Integer.max value. Why is input like this? Oh, it's this. Okay. All right, so what is going on here? So we probably want to print ants for each step. Okay, so we're saying, what is the room? It's 8 by 5. Initially, it goes from 2 to 7. Yeah, from 2 to 7. We want to place a width of 4, so we can't do above and below. Okay, so it goes from 1 to 4. We need a height of 2. C is minus 1. Y minus. The new y1 is 2 minus y1, which is 1. Oh, it's probably these are negative. Yeah, x2 minus x1. No, this should be y2 minus y1. Looks right. One minus 1, 2. Oh man. So this case I'm getting wrong. The middle one. This, okay. So I'm printing 0, the answer is 2. So it's in a room that's 1 tall, 8 wide, or 1 wide, 8 tall. This goes from 3 to 6. I go from 1 to 5. Shouldn't have removed these. What am I saying is possible? C and D. So this is the right section, yeah. So C we say 0. Why is that? So plus y1 or plus new y1 plus y1. So the new y1 is 3. What is the height? Oh, the height is 3. Oh, this shouldn't be, this should be height 2. Yeah. Okay. There we go. Took a minute. Should be good there though. All right. Yeah, that was like very implementation heavy. I guess it wasn't actually that bad. I don't know why I'm complaining. It was like 30 lines. Okay, anyway. Moving on. We'll listen for our verdict there. Alright, looks like we got it. Let's see. Alice and Bob are playing a game on a matrix of 2 rows and m columns. The cell in the ith row, in the jth column, is aij, or has this many coins in it. Initially, Alice and Bob are standing on a cell 1, 1. They're going to perform a sequence of moves to reach cell 2m. They can move right or move down. First, Alice makes all of her moves. until she reaches 2M. She collects the coins in all of the cells she visits. When Alice finishes, Bob starts his journey. He also reaches 2M and collects the coins in all the cells he visited, but Alice didn't. The score of the game is the total number of coins Bob collects. Alice wants to minimize the score, and Bob wants to maximize it. What will be the score if both players play optimally? I love game theory problems. Okay, so the idea here is you've got some squares like this, and Alice is going to take some suffix here and then some prefix here. So now Bob will get, well, Bob either gets these or he gets these, right? It's that easy. So if Alice goes like this, then Bob can't get any of both, right? So Bob either gets these ones or he gets these ones. So what is the score if both players play optimally? So we just try every combination of these Z's, that easy. So we have suffix sums on the top and then prefix sums on the bottom. Yep, we can do this in like 4 minutes. So we read A and B, I guess this probably needs to be long array, huh? Yeah. Long array prefix for ACS equals new long array n plus 1. And then BCS equals new long array n plus 1. For int I equals 1 less than or equal to n, I plus ACS at I equals ACS at I minus 1 plus A at I minus 1. And then for int I equals 1, I is less than or equal to n, I plus BCS at I equals BCS at I minus 1 plus B at n minus I. Okay, and then long ants equals 0 equals long dot max value, sys out ants. For int split equals 0, split is less than n, split plus plus, so we'll brute force where we go down. A take will be split, and B take will be n minus 1 minus split. And then ants equals math dot min of ants, or ACS at A take plus BCS at B take. There we go. Then print it. Should be good. No, what? What? So Alice wants to. Oh, we have these backwards. So you 7. How do you do 7? Oh, this is not add, this is math.max. Because Bob doesn't get both, he only gets one of them. Easy problem. Alright, awesome. Gotta love it. Gotta love it. Alright. I'm moving on. I'm very confident in that. Yeah. Say no to palindromes. Let's call a string beautiful if it does not contain any substring of at least length 2, which is a palindrome, which means it doesn't have any substrings of length 2 or length 3, because a substring of length 4 will have a palindrome in the middle. That's something you'll learn after you forget it for a minute. Okay. Recall that a palindrome is a string that reads the same from the first to last as last to first. We know what a palindrome is. Thank you very much. Let's define the cost of a string as the minimum number of operations so that the string becomes beautiful. So that a string becomes beautiful if in one operation it is allowed to change any character of the string to one of the first 3 letters of the Latin alphabet. Does it always contain? Yes, okay, so it's all A, B's, and C's. You are given a string S of length n. Each character in the string is an A, B, or C. You have to calculate M queries. Calculate the cost of the substring from this to this inclusive. Okay. So here we go. Where is my pencil? Here we go. Here's my pencil. Okay, so we have some stuff going on. So if it's, well, you have an A. If it's 1, it's already beautiful. Okay. If it's 2, you can't have AA, but you can have AB. So let's say you have AB. If you have 3, you have AB. You can't put an A here because this makes a palindrome. You can't put a B here because this makes a palindrome, which means you have to put a C. And then these previous 2 are forced, so you gotta be A, B, C forever. There you go. So that's your string. Okay. So there are 3 ways of doing it, right? Or yeah. There's A, B, C. No, there are 6. There's A, C, B. There's excuse me. There's B, A, C, B, C, A. And then there's CAB and CBA. So we have these 6 ways. We can check each of these per query. We just need to know a prefix sum of every 3 characters. Is like whatever is something. Yeah, so we'll say like if we count ABC, 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 how many mismatches do we get in this range? Okay, yeah, and then we'll try each pair of 6. Okay, so that's the idea. Let's do it. What do you say? So yeah, so this is n. Oh, single test case now. Nice. Int n equals this. Int n queries equals this. Alright, then we'll read char array line equals this dot to char array. And then we'll say for int equals 0 less than n queries plus, and then handle the query. Alright, so now we need to build a prefix sum array. So we need int array prefix sum. New int array. Let's make it 3 by n plus 3. For int I equals 0 less than n, or I equals 3, I is less than or equal to n plus 3, I minus or I plus plus. For int char equals, or c equals 0, c is less than 3, c plus plus. Someone mentioned a good language I should switch to over here. Alright, so prefix sum at this character in this index equals prefix sum at this character in this index minus 3. And then if line at I minus a is equal to this character, then prefix sum, sorry, this is I minus 3. Prefix sum at ci plus plus. We can clean this up a bit by just doing that. Yeah, no, we can't. The way I did my for loops doesn't work, but that's fine. Okay. So now we have these prefix sums. Alright. So let's make a helper method here. Static int count x in. So we'll have an int L, int R, and then we'll have a int char, or I guess int C, and then also an int offset. Yeah, and then we need our int double array prefix sum. So this will, in the substring from L to R, if C is the offset, or if C first starts at offset, count num of occurrences. It's not how you spell occurrences. Occurrences, I don't know how to spell occurrences. Okay, whatever. We're not going to worry about that. Times it appears. There you go. If you don't know how to spell a word, just use a different one. Of course, I do know how to spell the word number, but we'll move on. So, yeah, handling this offset is weird. So let's say L plus equals offset. Good. All right. Now, we want to set the right so that its value mod n is equal to L mod n. So R minus equals R minus L. Plus 1. Okay, so I guess int length will be R minus L mod n mod 3. So we want the length to be divisible by 3. If it's not, we need to make R smaller. So R minus equals length mod 3. If the length is 1, oh, we want the length to be 1 more than a multiple of 3. Oh, plus 1, okay. I guess just R minus L. We want the difference in these things to be a multiple of 3. So this, yeah, what does this mean? We have this position, this position, this position, and this position. So this is L, this is R. So either they're the same, or they differ by 3, or they differ by 6. Yeah, okay, exactly. So R minus equals R minus L modulo 3. Okay. We don't need length. And now we can just say return prefix sum at this character. This is going to be R plus 3 minus prefix sum at this character at L. I think that's that easy. Okay. So then we just need a static int count. So this will be int L, int R, some string like val, and then int array prefix sum. Okay, so then int res equals 0, which we return. So int c will be val.char at I minus a. And then in offset is I. So now res plus equals count occurrences in. We'll go from L to R. The character is C, the offset's I, and we pass in the prefix sums. Awesome. Okay, so now int ans equals integer.max value. Ans equals math.min of answer and count from L to R. Maybe we'll start with ABC, and then prefix sum. So this will be CB. Yeah, let's just do all 6 of these. Okay, so these start with B, start with C. Then AC and CA, and then we have AB and then BA. Yeah, I think we're good, right? We should be good. Okay, so this works. We have our answer, and then sys out. I guess we'll print it. So we need print writer. out.print line answer out.close. Nope. Exception. Array index out of bounds. Oh, wait, so this is C up to 3, that's fine. Less than n plus 3. So bounds 8. Okay, so yeah. So if L is greater than R, just return 0. I think that's one problem at least. What? What? Why? Okay, so I'm not going insane. The first query of the substring can be changed to this in one operation. Oh, this is count the number of matches. Okay. So we want mat.max. We want the max matches. And then we want R minus L plus 1 minus answer. No. Okay. Should be 0 then. Oh my goodness, we match it. Let's submit. There's a little bit of sketchy stuff going on here, so I'm not 100% sure this is right. But we have these beautiful lights to tell us. That is right. Okay, nice. Boring segments. We have n segments on a number line, numbered 1 to n. The ith of which covers all integer points from L to R, has a value wi. We're asked to select a subset of these segments, possibly all of them, and then once it's selected, it's possible to travel between 2 integer points if there exists a selected segment that covers both. A subset is good if it's possible to reach point M, starting from point 1 in an arbitrary number of moves. Okay, so if it's... So a subset is good, so we have N and M. Okay, is M the max? What is M? Yeah. So it ranges from 1 to 12, and we want to see if like it spans the entire thing. Okay. The cost of a subset is the difference between the maximum and minimum values of segments in it. Oh, so every segment has a weight. Okay. Find the minimum cost of a good subset. In every test, there exists at least one good subset. Well, you could kev everything, right? Yeah, so we can do a 2-pointer sweep on the segments sorted by y. If we have it, yeah, so here's the idea. So we have the segments sorted by value. So maybe here are some of the segments or whatever. They look like this, right? I don't know, whatever. That is a bad example. So we've got these. And then we have the cost. So if we sort the segments by cost, then we want to use a continuous range of the segments, right? So if we're using this segment and we're using this segment, maybe we need this one, maybe we don't, but it doesn't hurt not to have it, because the only thing we're paying for is the difference between the biggest and the smallest. So we can say, okay, we'll take this L, and then we'll continue moving our pointer to the right so long as we need to, because we don't cover everything. And then once we do cover everything, then we'll say, okay, well, let's move our left pointer over by 1. So now the question is, how do we check if we cover everything quickly? And this is where you stop thinking and just pull out the big data structures. So we can have a segment tree. We need range add. And then we need range min. So we can add one, I guess, and subtract one from a range, and then we can say what's the min across this range, and that will be exactly what we need. Okay, so yeah, there we go. Let's code it up. We'll start with the segment tree. So we need leftmost, rightmost, to prop, and then sum. Wait, to propagate, and then min. Yeah. So then public st, so we'll pass in int L, int R, leftmost equals L, rightmost equals R. How big are the values? So single test case up to 10 to the 6th, yeah, so we should be fine. All right. So if leftmost is not equal to rightmost, we also need a segment tree left child and right child. Then we need int mid equals leftmost plus rightmost over 2. L child equals new segment tree from L to mid, and then R child equals new segment tree from mid plus 1 to R. Then we'll need public void recalc. So min equals math.min of lchild.min and rchild.min. Then we need min, which returns min plus to prop, which is what the min looks like from the outside. And this is only if lchild is not equal to null. We'll do this. All right, so we have min, then we need prop, public void prop. At the end, we'll recalc. And then we'll say if to prop, well, I guess we'll just do this anyway. So we'll say lchild, or if leftmost is not equal to rightmost, then to prop equals 0, lchild dot to prop plus equals to prop, and then rchild dot to prop plus equals to prop. So we'll push it down and then set to propagate equal to 0, and then recalc at the end. All right, so that's the base stuff. Now what do we need? So we need void range add, int L, int R, and then int the amount we add. And then we need void range min, int L. I guess we don't need range min. Yeah, we'll just call this min method on the global thing. At the end of range add, we need to recalc. If L is greater than rightmost or R is less than leftmost, then we return because it doesn't affect us. If it covers us, then we can say to prop plus equals D and then return, because we'll absorb the entire thing here. Otherwise, we say lchild.range add and then rchild.range add. Okay. So we've got our segment tree that we need. Now we need our segment class. So each segment has an int L, R, and then cost. The segment has an L, and R, and a cost. So this dot L equals L, this dot R equals R, this dot cost equals cost. Then we need to sort them. sort by cost to o.cost. All right, so now what is this? We're just given n and then the number of points. Okay. Or the number of, wait, the number of integer points. Wait, am I misreading the problem? Once a segment is selected, it's possible to travel between integer points if there's a good selected segment that covers both of them. Oh, M is just the max size of the segment tree. Okay. Okay, so now we need a segment tree, or a segment tree st equals new segment tree from 0 to m minus 1. Yeah, we'll just offset everything by 1, because I like it that way. And then 4 into I equals 0. Oh, we need our segments. So seg array segs equals new seg array. We have n of them. Than n plus plus of seg that I equals new seg from this minus 1 to this minus 1 with the cost of this. All right. Oh, magic keyboard nonsense going on over here. So now we have our list of segments. We need to sort them. Now we have them sorted. Now we need to do a 2-pointer. So int l equals 0, r equals minus 1. So while l is less than n, l plus plus at the end. Okay. So now we need to do this segment tree stuff. While, okay, so if well is less than n and r is less than n, I guess. So if, I guess we'll just write this once and then fix it in a moment. So if st.min is equal to 0, then we need to increment r. So r plus plus, if r is greater than or equal to n, then break. Otherwise, we need to include the next segment. So st dot range add from segs at r dot l to segs at r dot r, add 1 to them. This needs to be a while loop. Keep doing this. Okay. All right, so now consider possible answer. The answer. Okay, and then we need to do st.range add from segs at l dot l to segs at l dot r by minus 1. Because we removed this thing. Okay, so now we need to consider this as a possible answer. So ants equals math.min of ants and segs at r dot cost minus segs at l dot cost. And I think we're good. No. Not even close. All right. What about this one? So that's 0. This one we're giving an answer that's too good. Okay. Oh man. Yeah. Because, so this doesn't work because everything does get, this is a good test case, thank you. So 1 to 5 hits this stuff, and then we hit 4 to 10, and then we hit 11 to 12, but we don't hit 10 to 11. So to fix this, we can just multiply everything by 2. Yes. So make this to 2 times m, I guess, or, okay, yeah. Let's think about this for a moment. So initially, it goes from 0 to 5. We want to make, so we have 0, 1, 2, 3, 4, and 5. So we need 0, 1, 2, so yeah, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10. So, okay. So we had from 0 to m minus 1. So m is 6. We need n minus 1 times 2. Yeah, so there's 6 things here. So we want 5 times 2 is the biggest. Okay. Then each of these goes from this times 2 to this times 2. Okay. Now we should be dealing with only integers, so we get the right answer. Looks good. So let's submit this, and then we'll move on to problem F. All right, good graph. We have an undirected graph of n vertices with weighted edges. A simple cycle is a cycle of the graph without repeated vertices. Let the weight of a cycle be the XOR of the weights of all edges in it. Yeah, okay. Let's say the graph is good if all simple cycles have weight 1. A graph is bad if it's not good. So if all simple cycles have weight 1, that's interesting. Okay. This is very, like, anyway, interesting. So a tree is always good, right? Yeah. Initially the graph is empty. Yeah, a tree is good, right? Because the tree has no simple cycles, so all none of them have weight 1. And then you might have some bad graphs. Okay, initially the graph is empty. Then Q queries follow. A query has the following type. Add an edge between vertices U and V of weight X if it doesn't make the graph bad. For each query, print whether or not the edge was added. Okay, this is hard. So let's, oh, are all the weights 0 to 1? Interesting. So we can do it offline if we need to. That might be important. Let's think about this. So we have 9 nodes, 12 edges. So we have 6 and 1. Initially we add this. This is 0. So we do add this, right? Yeah, we add this. Then we have 1 to 3. This is weight 1. So we add this. Okay. Then we have 3 to 6. This is weight 0. So now we have one cycle here, which is weight 0. So anytime two things have an edge between them of weight 0, we can union them together. Is that true? Yeah, that's true. But now we can't add anything to this component. Oh wait, we can? Yeah, we can. So, like a connected component always has two groups. Oh man, but it can be like a tree. And if it's a tree, there aren't any cycles. Okay, so maybe it's not trivial. So 6, 2, then this is 0. Okay, so we had that. 6 to 4, this is 1. We had that. 3 to 4 of weight 1. Oh boy. 3 to 4 of length 1. So that's a problem, because you can take this. So we don't add that, right? 3 to 4 of length 1. So if this is the sixth thing. 1, 2, 3, 4, 5, 6. Yeah. Okay. 2 to 4 of length 0. We add this? Why do we add this? So in this case we have, oh, because this isn't a simple cycle. What is a simple cycle? Simple cycle, the graph. A simple cycle is a cycle without repeated vertices. Yeah, I guess just barely. So I guess this is allowed. Okay. All right. So this was the 4, 2, 2, 4. Okay, now we have 2, 5. 2, 5 is 0. 4, 5 of 0. This is a no, because we've got a cycle here. Yeah, so this is a no. So then we have 7, 8. This is a 1. 8, 9. This is a 1. And then 9, 7 as a 0. So this is a no. Yeah, okay. So I understand the problem. The question is, how do we do it? Well, the first question, how big are the bounds? It's 3 times 10 to the 5th, 5 times 10 to the 5th. And the queries are the edges we add. Yeah, okay. So the question is like, which edges end up existing? So we need to two-color the graph at the end, right? Like this is valid, so we don't really two-color it. Like, kind of, but not really. Yeah, so we've got these articulation points. This is an articulation point. This is an articulation point. So we want to say, yeah, this is tricky. All right, thinking time. In other words, Cliff Bar time. Can you have a loop from yourself to yourself? Yeah, you can. Kind of. Like yourself is a... Combining nodes doesn't work too well because this graph here, like we have this thing where it's like this. We have this cycle and then we have this cycle. And it's like if you split this node in half, it would break, right? Each cycle on its own is fine, but if you split it in half, it breaks. If you were to make it like this, even though you can like kind of consider these the same node, at this point, these are now two different graphs. These are not equal at all. Tourist, nice job, man. Geothermal's doing pretty well too. He's quick, at least. So if all simple cycles have a weight 1, well, if we were to do this naively, does a spanning tree matter? Maybe. Like, there are edges outside the spanning tree that do matter. Like, the fact does this edge actually affect anything? Yeah, it does. Because this edge prevents us from adding this of weight 0. Oh, like if you were to ignore this part. So like, what's the question? Can I reach... Well, what is any cycle? So you go down from the root, you hit some node, then you go around, and then you hit the same node. So this part will cancel itself out. Is this the same as... We want to know if there are any even cycles. Are there? So we'll root the tree here. So what is the distance to everything? So this is distance 1. This is distance... what distance is this? This is distance 0. This is distance 0, 0, and 0. So now we look at every edge. This is 1 between 0 and 0. That's okay. But now that introduces an additional constraint. Like, we can't ever combine these in the future because we have like a back edge. Yeah, once you have a cycle, you can't ever do this. There are no duplicate edges, right? No multiple edges. So you can never have, so it's a cactus. It's a cactus. Ladies and gentlemen, it's a cactus. Cactus. Cactus time. It's a cactus. It's a cactus. Oh, it's a cactus. Man, I feel like a genius. I feel like that isn't really that impressive of an observation, but the fact that I just got it, ooh, feels good. All right, so we've got a cactus now. Yeah, because if we have any non-cactus, then we have something like this, right? And now this is a problem, because if we have this and we have this, then we have this. And we know these things have the same parity. All right, boom, boom, it's a cactus. All right. I feel really good about that observation. Just I feel so smart. Okay. All right. So we have a cactus. Is any cactus legal? We need a cactus, but there need to be an odd number of ones in each cycle. Is this dynamic cactus? It's cactus with additions, right? So we need, yeah. So we need cactus, and we need how many ones are in a cycle. And then the things will get combined. Yeah, we can do this problem. 51 minutes, that'll take us 25, maybe 30. So, oh man, this is, I feel so cool. Who wrote this set? Goodness. Was it Vuv? Vovu? Awoo. Man, bro, nice job. Oh man, it's this guy. I think he did some of these Russian ByteDance camps, maybe? I think. Maybe not. Okay. Maybe I could be misremembering. Might be somebody else. That is a good set. Oh, this feels good. Okay. Cactus. So how do you do cactus stuff? So we have some edges. Okay, we add some stuff. All right, now we add some edge. If these were previously connected, oh, we need to be able to figure this out kind of fast, don't we? Link cut tree, maybe? So, yeah, so we need to see, okay, are they connected? Maybe, so this might be harder than I thought, but it's going to be a bit messy. So we have some stuff that exists. Okay, so now we need to see, are they connected? Are these things connected? Okay, if they are connected, or if they're not, so no, then we just add the edge. Yes is when it's tricky, because this is like maybe a cactus edge, like maybe illegal. So then the question is, we need to look only at this path. So we need to say on this path, are there an even or odd number of ones okay, and then also like does the path include any non-bridges? Yeah. Okay. And then we need to remove all of the bridges. So then we need to like add the edge. So, oh wait, we could just do link cut tree. Yeah, so we can do link cut tree. So this add edge, yeah, okay, I think I got it. I don't know why I feel so excited to solve this problem. It's just like, feels good. Cactus problems are always just like wacky hard, and this one I feel like is just approachable for whatever reason. I really like this problem. I've gotten more enjoyment solving this problem than I have solving a lot of problems recently. This is just a great problem. Okay. Okay. It's also so unique. I feel like it's unique. Maybe it's not, but it's good. It's good. Okay. So we say we want oh wait. Yes. So we can do a tree query here, because this can be a spanning tree. And then any non-bridges. Yeah, because we'll mark them all as non-bridges. Boom! I got it. Okay. Yes, sir. Okay. All right. So I'll talk about the solutions after we've coded it, but we're going to need a link cut tree. So for this, we need a splay tree. And then we need one for each node, one for each edge. And then what operation do we need? We need range sum. And then we need range, like, range kill, I guess. Yeah. Okay. All right. Oh, I'm so excited to solve this problem. I really cannot wait. Plus, it's the last problem in the set, which makes it even more fun. All right. So we need splay. Display tree. Okay, so we need the data. Static class data. So toProp is just going to be whether we kill everything, right? Yeah. Kill, I guess we can call it. So this is just whether we've killed everything. And then our data will be, so this will be int killed edges, and then int odd nodes. Public data killed edges, int odd nodes. This dot killed edges equals killed edges. This dot odd nodes equals odd nodes. Is there a time limit decent for this? 2 seconds. Ah! Please don't roast me on this. Okay, so this is going to be a data. Yeah. Odd nodes. Every node. Is it every node or every edge? Oh, this is only on the edges. Okay, so this is, yeah, int odd. All right, so we can do this. So this is display, well, sure. Wait, what is a display tree here? So we need a data sum, and then in size. And then I guess probably a data for me as well. Call it data. So this dot sum goes okay, and then to prop equals false. All right. What's wrong with this? Declared static. Redo propagate. Okay. So this is, so if not x dot flip prop, no, x dot prop kill. All right, so flip prop, we handle the flip. Okay, so if x dot kill prop or prop kill, we also need to recalculate, so we need to do this too. All right, so if we propagate a kill, this matters. Okay, so this part we need to just do anyway. Yeah. Now we have this part. So this is our sum, right? Yeah, so data sum will be x dot data. Oh, this is just sum. X dot sum. Well, let's say data sum. Yeah, okay. So now we need a static data combine data A, data B. If A equals null, return B. If B equals null, return A, return new data. So this is killed edges and number of odd edges. A dot killed edges plus B dot killed edges, and then A dot and odd edges plus B dot and odd edges. I think it's that easy. Okay. So propagate a kill. Yeah. How do we do this? Okay, so we need to propagate this to our kids. If we've propagated a kill, then if x dot, well, okay, we also need to like boolean is edge, right? fix a lot of it. Okay, so if we combine, then this is a dot n edges plus b dot n edges. Okay. All right, so if we've propagated a kill, so now we might need to handles the flip propagation. Okay. So if we need to propagate a kill, if x dot data dot n edges is equal to 0, or is not equal to 0, then x dot data dot killed edges equals x dot data dot n edges. Inside me. Okay. Yeah. So kill me. And then x dot prop kill equals false. Then we also have to kill all of our children's edges. So for splay kid in x dot kids, if kid is not equal to null, then kid dot prop kill equals true. And then mark our propagation as false. So yeah, so we kill our own edges, then kill, or like propagate children, and then we're done with that. Okay. So then this is our data. Yeah, that's fine. Yes, this is what we do here. Now we need to recalc. Okay. This is nice and clean, I think. Yeah? Yeah, nice and clean. Okay. Recalc. Our sum. Why do we need a sum? I don't think we do need a sum. Oh, we do need a sum. Yeah. Okay. So sum equals our own data. Am I doing anything with that here? No. So our own data, our size equals 1. So size plus equals this. We can recalculate the size whenever we want. That's the easy mode. For sum, sum equals combine. X dot sum, kid dot sum. Okay, I think we're fine there. Yeah. Okay. All right. So we have our splay tree, possibly right. We do need that. Skip the values other than sum, recalc. For values other than sum, change for cut and prop. Yep. Skip path parent. We have those. Okay. So now we need link cut tree. Does this need to be? Oh, yeah. Wait, was that important? Is it that easy? Oh my goodness. It's that easy. Okay. Thank you. Okay, good graph. So we have some stuff. We have an undirected graph of n vertices with weighted edges. Simple cycle with our okay, let weight be of the cycle be the XOR of the weights of all edges it consists of. Yeah, so this is n and then m. Okay. So splay array nodes equals new splay Okay, we need int n equals this, and queries equals this. So this will be n plus n minus 1. We'll have the nodes and then the edges. Okay. Then for int qq equals 0, qq is, oh, we need to make each node first. Yeah, so int cur edge will be, cur edge index will be 1. No, it'll be n. Okay, and then for int I equals 0, less than n plus plus. Nodes at I equals new splay. What do we need here? The data. New data. What do we need here? Killed edges. Nothing, nothing, and nothing, because it's a node. All right, awesome. So now we need to handle the queries. So we read from to and then wait. So from this to equals this, wait equals this. Yeah. These both need to be -1. Okay. Oh, we also need range update. Okay. Yeah, so well, we'll do that in a moment, I guess. Yeah. Okay. So to do, check if the range sum is or uses an odd sum, and then check if the range sum uses any killed edges. So we want data range sum equals path. What did I call it? It's path query, right? Path aggregate. Path aggregate from nodes at from to nodes at to. Oh, I guess if it's not connected. So if not, okay. If connected, what's it called? Okay, so fine. Display root 1 equals nodes at from dot find root. Come on, what's it called? Find root. Oh, link cut tree. Well, we'll just make all these public. Okay, so this connected one. Display root 2 will be find root of nodes at 2. So if root 1 is not equal to root 2, then yeah, then this is definitely okay. So then we want display edge will be nodes at cur edge index plus plus. Connect. Link. Yeah, because it's link cut tree. Link from root 1, or link from, sorry, nodes at from to the edge, and then link from edge to nodes at 2. Okay, and then sys out, yes. Okay, so otherwise we need data aggregate, or data, what's it called? Data path, or range sum equals path aggregate. Oh, we need to, this is annoying. Okay, so how do we do this? So I need to how do we do path sum from A to B with link country? So we need make one of them the bigger, access the other. Yeah, so display A equals nodes it from B equals nodes at 2. Make root A, and then access B, and then A dot sum should be the path aggregate, right? Yeah. So, or we can just do path aggregate. So data range sum will be path aggregate to B. Okay. Yeah. So if range sum dot killed edges is not equal to 0, or range sum dot n odd edges mod 2 is equal to 0, that means this is a bad edge. So sys out, no. Otherwise, sys out, yes. And in this case, we need to range kill. So how do we do that? We need to range kill. So we can access B, and then we can say A dot range or A dot kill proc kill equals true. I think that's it. Odds this works near 0, but it would be so cool if it did. No pointer exception. Did I just break it? Oh, because we never, yeah. New display. So new data, what do we need? The number of killed edges. How many killed edges are there? 0 initially. Number of odd edges. Oh, so we need the weight. Weight. Yeah, I guess just weight. Interesting. Okay, and then the number of edges is 1. I'm so close. I am literally so close. I get this one case wrong. Ugh. Okay. Alright, so we need some debug here. So this is not connected, so we'll add the edge. What about this? Can you just skip the last 3, and now if we do that, the number of edges is 6. and so 6 and then 9. So what's going on here? Okay, 6, 1. This is 0. And then 1, 3. Not connected, adding edge. 1, 3. Not connected, adding edge to 1. Okay. 3, 6 is connected. Range sum, killed 0. Yes, okay. So we want to kill. So we kill this, and then we kill this. So now we have, I guess let's bring these here. So 6, 2. So then we have a 2. Edge is 0. Okay. Next one is 6 to 4. Not connected again, we had a 0. And then we have 3, 4. So 3, 4 is connected. 0 people killed. There are 2 odd edges. Oh yeah, this is, okay. So here's the problem. This shouldn't be is not equal to 0. This should be is not equal to, if this is equal to weight. Yeah. Okay. Looks right. Print, writer, and submit. Let's go. Wrong answer, test 1. For real? Did I? Oh. Ah! Oh boy. Oh boy. Okay. All right. Yeah, that's not even okay. Alright, debug equals true. So we want back to this. Yeah, I guess we can just look at this. This is fine. So little overzealous there. So we had 6, 1, that was a 0. 1, 3, 2. Or 1, 3, that was a 1, that's fine. 3, 6, 0. That's good, so we kill it. 6, 2 was a 0, unconnected. 6, 4, this is a 1. Okay, then 3, 4. Two killed. Or wait, there shouldn't be 0 killed. There should be these 2 that are killed. Oh boy. Oh, okay. So if the other thing yeah. Dot sum dot killed edges. I think we always prop before we recalc, so I think that part's fine. Plus killed edges of x. Then what is this? This is n odd edges. X dot sum dot n odd edges. X dot. Oh, this is kid. And then this is kid dot sum dot n odd edges plus. And then this is x dot sum dot n edges, and then kid dot sum dot n edges. Should be plus again. Okay. Yeah, that's better. right? Oh, bro. For real? I don't think we use this anymore. Huh, okay. So we link these two up. How many killed edges? The number of odd edges is just your weight, and this is 1. Okay. So this is always true. Otherwise, we have these two nodes. We make A the root. We get the path aggregate to B. Oh, this is not right. How does path aggregate work? Yeah, so this is this should be b.propkill, I think. Watch me get Javad. Bro! It's the right solution! Ridiculous. This is ridiculous. It's ridiculous. It's ridiculous. So bad. Okay. Alright, how do we... Okay, where's the tip prop? This is the right solution, man. It's in log n. It's in log n. Okay. This is fine. This is fine. Okay, so it's the so it's maybe it's the data. Okay, this is, we don't need this, 0, 0, 0. I don't think we need this. Killed n odd n, okay. And then this is, oh boy. Path aggregate B, maybe path aggregate. We'll do this in a minute, okay. So what is this? This is, we do that in a minute. This is the hard part, okay. So x dot sum killed edges equals x dot data killed edges, x dot n odd. Okay. X dot sum n edges equals x dot sum n edges plus kid dot sum n edges, x dot sum killed edges equals x dot sum killed edges plus kid dot sum killed edges, and then x dot n odd edges equals x dot sum n odd edges plus kid dot sum n odd edges. Okay, and then if kid dot prop kill kid dot sum n edges, otherwise kid dot sum n killed edges. Okay, I don't think we need this anymore. What's this? X dot n x dot data n edges is not equals 0, data n now we'll bring this data back. Where's the data? Data, where's data? Oh, that was fine. Running out of time. Okay, where is this data? Data and edges. Okay, then we need here, we need this data, please. Okay, and then v dot sum. What? Oh, v dot data. V dot data killed n edges, or v dot sum killed edges. V dot n odd v dot data n edges. Is this the right order? Sum killed sum odd, and then sum and edges. Okay, do we pass? All right, any other wacky optimizations? So we can make this and 1, find modulo. Is there really no modulo in here? Never doing mod 2, okay. That's not gonna help anything though. Tilly. 24. Okay, so we're doing something. So, bro, this is ridiculous. I'm about to just rage quit here. Give me a bigger time limit. I don't even know what to say. How do I speed this up? I thought I was doing a good job. I didn't think it was that slow. Make the things when we need them. We link these two. Those are both necessary. I guess we should, but the access will run in like no time at all. Okay, what does path aggregate do? I guess we don't need this access. Yeah. Very annoying. This is really annoying. Is my propagation too slow for some reason? Prop? I never call prop inside prop. I never call any methods inside props. This is sort of one. This is ridiculous. Make bigger time limits. It's n log n, bro. It's n log n. This is infuriating. I'm just upset right now. I feel cheated. I should have this. Okay. All right. Well, I'm not getting it, so solution time. I have the solution to it. Solved it. Got the big brain activity over here. She's in the wrong language. I think this is just right. I think in C++ this would just be fine. Yeah, maybe if I have some extra time tonight after work, I'll just convert this to C++. Okay, solutions. Solutions real quick here. All right. So, problem A. Yeah, so for problem A, the input that they're given is actually like super convenient. Like, it's really nice because, so all of the slices you're given are even, right? So you can just like combine two slices into one. So you're given 6, 8, and 10, I think, are the size, yeah, the pieces are size 6, 8, and 10. So you could just make them sizes 3, 4, and 5. And then anytime you have an odd number of slices in the original problem, you just round it up to the next even number of slices. Because you can only ever make even numbers of slices. So basically, let's just say you make 3, 4, and 5 slices. And then the baking time takes 15, 20, and 25 minutes. But each of those are divisible by 5. So 15 over 5 is 3. 20 over 5 is 4. And then 25 over 5 is 5. So 3 slices takes 3 minutes, 4 slices takes 4 minutes, 5 slices takes 5 minutes. But really, you just multiply your answer by 5 at the end in order to fix it. So yeah, that's the idea. Now the question is, you just have to say what is the smallest number you can make that's at least as big as what you need. And then making each number costs just whatever that number is. So you can make 3, obviously. You can make 4 and you can make 5. You can also make 6 by making 3 twice. So 3 plus 3 is 6, so you can make 6. And then for any bigger number, right, so you can make 6 here. You can also make 7. 7 is just 4 plus 3. And then 8 is just 5 plus 3. So for any number, you can just repeatedly, you make 3, 4, or 5, and then after that, repeatedly make groups of 3. And then, you can make any number you want and exactly the number of steps that it takes, unless that number is 1 or 2. And 1 or 2 you have to make with 3 steps, because 3 is the smallest number you can make. So yeah, that's the idea behind the problem. Code is pretty simple. Looks like this. You divide n by 2, round it up. If it's odd, take whichever is bigger, enter 3, and then print that number times 5. And that's the solution. You can do this all in one line if you want, but yeah. Cool, so that's it. Let's move on to problem B. 2 tables. So yeah, you've got 2 tables here in a room. You want to place this green table in such a way that it fits inside the room and also the blue table fits inside the room. But you have to move the other table the smallest amount possible. You can move it, you can like slide it, but you can't rotate it, and you can't rotate the green table either. So yeah, the key observation here is that there are only 4 possible ways to do it. So you can have your tables look like this. I'll say the white one is the one that was initially there. You can have them look like this, or you can do the other 2 ways, which would be you have the white one to the left or to the right. So these are the 4 ways of orienting the tables. And in this case, the only direction you'd move the white table is down. Here you'd move the white table possibly up. Here you would move it possibly to the left, and here you'd move it possibly to the right. So if you calculate each of these individually, they're not very difficult to handle. But basically, in order to do this, you'd say, okay, the top of the room would be here. I'll just show you how to do it for this example, and then you can extrapolate. The top of the room would be here. We know the height of the table we're trying to place. That's this much. And we know the white table started off, maybe it started off here. So we only need to move the white table down. The distance that we need to move it is whatever this distance here is. So you do some addition and subtraction and stuff, and then you can get that distance. I'll show you the code. If you're confused with any of the math, this should explain it. But basically, the important part here is we get the width and height of the table we're about to place, and then I have the width and the height of the table that already exists, and also its original coordinates. And then from that, I do all 4 cases. It's also possible you might not be able to place the 2 tables like left to right if they don't fit like that, if they wouldn't fit in the room like that. So if that's the case, then you skip it. And it's also possible you can't place the tables at all, in which case the answer is -1, so just handle that accordingly. Yeah, I mean, I guess a lot of what I'm saying is just do the problem, but there isn't much thinking involved here. It's just make sure you get all 4 cases. So yeah, that's it for problem B. Problem C, coin rows, pretty cool problem, I thought. It's a game theory problem. The way it works is you have 2 rows of coins. So we'll use the first sample here. 1, 3, 7, 3, 5, 1. So Alice is going to start here, and first Alice is going to take some path through the coins, so maybe she takes this path here. In this case, she will use up all of these coins, and then her turn is over. Now it's Bob's turn. He also has to take some path, and his path again can only go right and down. And he wants the coins that he gets, which Alice didn't, to be as big as possible. Alice wants the coins Bob gets to be as small as possible. So the question is, how many coins can Bob get if he plays optimally? So in this case, Bob will get, if Alice made this move, Bob will get 7 coins. He can either get 7 if he takes this path here, or he can get 3 if he takes this path here. 7 is obviously better because he wants more coins. He can't get both of them because he would have to go down, and then later on he'd have to go up, or he'd have to go right and later on go left, and he can't go left or up. Okay, so what should we look at here? Well, if you notice Alice's path, it's going to look something like this. She's going to move right a bunch of times, maybe 0 times, then she's going to move down, and then she's going to move right a bunch of times. The coins that will be left over are the coins that are over here and over here. So Bob can't get any coin, he gets either one of these or the other, or he can get like half of the ones from the top, but since they're all positive, he'll want all of them. But he can't get both in any way. Because once he's on the bottom row, he can't go back to the top row, and once he's at this column, he can't get any of the coins to the left of that. So the question is, Alice knows Bob's going to get whichever one of these is bigger, the max. So Alice will just make her decision in order to minimize what Bob gets. And there are only n decisions that Alice can make, so we can consider if Alice makes each decision, what will the outcome of the game be? Obviously, Alice is going to choose whichever outcome is best for her, which is the one that's worst for Bob. So, yeah, that's the idea. We can just brute force what these look like, and now the only part of the problem that's left is how do we do this fast enough so that we don't TLE. So the idea here is that we're going to brute force the time that Alice goes down. So let's say Alice goes down at this time. That means we want the sum of these elements, we want the sum of these elements, and we want to see which one's bigger. In order to do this fast, we can pre-compute for every suffix what is the sum of each of these. So for each of these suffixes, what's the sum of each of these on the top row? And then for every prefix on the bottom row, what is the sum of each of those? And you can pre-compute all of these suffixes in linear time. So what that looks like is this here. So we can compute for, I flipped them, but for the one on the bottom, we compute all the prefixes, and for the one on the top, we compute all the suffixes. Yeah, so in this case, B is actually on the top. And then we brute force the split. On the top, we will take split items, and then on the bottom, yeah, this is really confusing the way I name my variables, but just ignore that, I guess, for now. I assumed that you read in the bottom first, but really you read in the top first. That's why this looks confusing. So then you will take split things from the top, and you'll take n minus split things from the bottom. Or I guess vice versa. Yeah. So you take a prefix of one, and then the ones you don't take you take from the other, and then Bob takes the max, and then that's one candidate answer. You take the best answer for Alice among all of them. Print that. All right, that's it for B. It's that easy. Okay. Yeah, my code for that might be a little messy. Okay, for problem D, say no to palindromes. This is a classic problem. I think I've seen something similar to this in an @Coder beginner contest. So if you've done those before, you may have seen this general idea. But here's what the problem is. You've got some string of A's, B's, and C's, and you want to say for a bunch of different queries, maybe your string is like A, B, A, C, A. For a bunch of queries, maybe we say for this query here, for this string here, how many characters do we need to change so that there are no palindromes in the string? In this case, there currently is a palindrome. There's this one here. So we can change this A to a B, and then we would have B, A, C, B. And now we have no palindromes. This doesn't have any palindromes. There are no palindromes of length 2 or length 3 or anything, or length 4, which means there are no palindromes in it. I guess there are always palindromes of length 1, but you can't avoid those, so we will ignore that. So the answer for this query would be 1. There's one character you have to change. And then same thing for this query, there's one character you'd have to change as well. We have to answer a bunch of queries for the same initial string, and we want to answer each query in order 1 in constant time. An important constraint of this problem is there are only 3 different types of characters. If there were 4, this would get much harder. But for 3, we can abuse it. So here's the important part here. Let's first notice that if you have any palindrome of, like, say this is one of length 5, we have a palindrome of length 3 as well. So instead of trying to worry about all palindromes of any length, let's instead worry about palindromes of length 2 and length 3. Similarly, if we have a palindrome of length 4, right in the middle there's a palindrome of length 2. So what we want to do is we're simplifying the problem. We only need to worry about removing all palindromes of length 2 and 3, because if there aren't any of those, then there are no palindromes at all. Okay, so we're doing this. How do we do this? Let's look at some strings here. So let's say we're going to build some string. It can start with A, B, or C. Let's just say it starts with A, because it doesn't matter. Then for the second character, we could pick A, B, or C, but if we pick an A, then it's like the same we have a palindrome already. We'll have a palindrome of length 2. So we have to pick a B here. Or we could pick a C, but again, it's like the same thing. We could just rename B and C. So this is our only choice for like these first two. Then for the third character, we have 3 choices again. We have A, B, or C. If we pick an A, we have a palindrome. So we can't pick an A. If we have a B, we have a palindrome here. So we can't pick a B. So we have to pick A, B, C. In fact, if you have 3 characters in a row, the only way for there to be no palindromes is if they're all different. What if we have 4 characters in a row? Well, we have this ABC initially. Let's say this is the 3 it starts with. After that, this 4th character, it can't match this B, because this would be a palindrome, so it can't be a B. Can't match the C, because this would be a palindrome, so it has to be an A. So if we have some really long string, right, and then you can make the same argument for this character. It can't be an A or a C, so it has to be a B. If we have some really long string, the only way it has no palindromes is if it looks like this. If it's ABC, 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 or it could be something else. It could be like ACB, 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 or any permutation of ABC, but it has to be repeated. So this means since there are only 3 permutations, there are only 3 factorial possible substrings of a given length that have no palindromes. We're going to see for each one of them what is the difficulty of turning it into that. And that's the solution. So, okay, cool. So we have that. How do we check if we have some string of length 6, maybe it looks like A, C, B, 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 for instance. We want to turn this into, let's say we want to turn it into ABC, ABC. We might want to turn it into something else, but we're going to brute force what we turn it into. Let's say for now, this is what we're trying to turn it into. We want to very quickly be able to say how many changes do we have to make to it in order for it to match this new string that we're trying to make. In this case, the correct answer will be 4. So there are 4 positions that don't match. In other words, there are 2 positions that do. And this is not going to be the best. You can definitely do it in at least 3. Yeah, so you can do it in 3. Well, maybe not. This might be the best. I don't know. I'm not sure. Yeah, you can do it in 3. If you had BAC, you would only have to change this one, and this one. But it doesn't matter. So we would try BAC later. For now, let's see how do we calculate the cost of ABC. What we want to do is we'll count the things at every 3rd step together. So what we want to do is say, like, if you step by 3s, how many of these things at these positions are A's? And then we want to see, okay, how many things at these positions that I'm circling in blue are B? And then finally, how many things at these positions here in white are equal to C? So we can do this with a prefix sum array. We can split the array into groups of 3 and then calculate what is the prefix sum of A's, of B's, and of C's, each of this value mod 3. So I'm going to draw this out slightly differently. So the array that we were given was A, C, B, 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 right? Let's draw it out instead like this. So we'll draw it out as A, C, B, B, B. And then for each of these arrays, we'll calculate the prefix sums. So we'll say, in this prefix, how many A's are there, how many B's are there, and how many C's are there. You have to be a little careful with the math. It's a little bit annoying, but it's not too bad. And you can calculate, if you take steps of 3, how many A's will you hit if you go from here to here. So that's the idea. Yeah, and that's the solution. So you just do that. So what I'm doing here is I make this prefix sum array. So this first character is, am I looking for A's, B's, and C's? And the second is, if I took steps from 3 since the beginning, how many of whatever character I'm looking for would I find by this position? So I calculate that here. You take your step 3 back, it's the answer for that, and then if this is the character you're looking for, then you add 1 to this part, because you see 1 more of it. And then for each query, I try all 6 possible strings you can make. So that's these parts. So I try each of those. I just try it with this method. So what I'm trying to do here is trying to maximize the number of characters that match what I'm trying to make. And the rest of them I have to change. So this is the length. So I have to change all of the characters minus the ones that match. And that's the answer that I print. So to see how many match, I say, okay, I want to look at the things that's first in the string, second in the string, and third in the string. Count how many of those match, add them all up, and that's my answer. So I do that here. And then this is the part where I use my prefix sum array. So it's a little messy, especially if the length mod 3 isn't 0, but it should be handled here. Okay, cool. That's the solution to problem D. 2 more problems, E and F. So for problem E, boring segments, I'll talk about the problem for just a moment here. So you have a bunch of segments. Maybe the segments go from 1 to 5. So maybe we have this, we've got this, this, and then this, for instance. And then each segment also has some weight. So maybe it's like weight 1, weight 5, weight 3, weight 2, and then weight 4. So now what we want to do is pick some of the segments. Maybe we pick the ones I'll highlight in green. This one, and this one. And we want to pick segments so that they cover all of the points between position 1 and position 5. Now, there are a lot of ways to do this, right? We might pick these 3, we might also pick 3, we might pick both 3 and 4, we might pick all of them. But we want to do it in such a way that we minimize the maximum difference between any 2 weights. So in this case, we're minimizing the 5 minus the 1. This is equal to 4. So our answer here would be 4, because that's the best way of doing it. And in this case, you don't have much choice. You have to pick the 1, you have to pick the 5. Whatever else you pick doesn't really matter. But yeah, that's the solution. So this is the problem. The next question is like, how do you do it? And the idea is that if we sort the segments by their weight, so if we have the segments sorted from like, okay, this is the segment with weight 1, then we have the one with weight 2, then with weight 3, then with weight 4, then with weight 5. In this case, the ones we picked were 1, 2, and 5. But we could have just as easily picked all of these elements. Like, the cost for it isn't any worse than picking 1, 2, and 5. Because if we pick 1 and 5, we might as well just pick everything in the middle because we get it for free. So the question is basically like, if the smallest, we can think about it like this. If the smallest thing we pick is 1, how big do we have to pick things before we can reach all the way across? And then we can do a 2-pointer sweep with this. So we'll say, okay, if the smallest is 1, how far do we have to reach? What if it's 2? How far do we have to reach? Etc. All the way up to if it's 4, how far do we have to reach? And then if it's 5, how far do we have to reach? And we need to check, okay, for this right endpoint, if we look at this range, will this get us to the end? If it will, then we're set. But if it won't, we have to increase our right endpoint until we can get all the way to the end, or until we fall off the end of the array and determine that it's impossible. So yeah, that's the solution. In order to actually implement it, you can have a segment tree. So you can have a segment tree where you want to store like how many times is each position covered. So that's what the segment tree is storing. And you can like handle that by when you include a segment, you add 1 to a range. And then when you exclude a segment, you subtract 1 from the range. And then you want to say, what's the minimum of all of the elements in the array? So those are your elements. So you have a segment tree. The segment tree has range plus equals 1. You have range minus equals 1. And then you have range min. All right, that's the idea. Yeah, so with those operations, you can say, do you reach all the way across? Because you just want to say, is every element covered? I guess there's a slight additional part that makes this a little bit harder. It's not too bad, for sure. But like, one part of the problem is like if you have, let's say you have this segment, and this segment. You have to be a little bit careful in this case, because the way these segments work, you can't pick just this segment and this segment to get all the way across, because you can't get from 2 to 3. So you can handle this by multiplying everything by 2, and then what you'll have something where it goes like 2, 3, 4, 5, 6, 7, 8. So now your segments will look like this. Here it's obvious, if you just pick the first segment and the last segment, you'll miss 5. So by multiplying it by 2, you handle the in-between numbers position as well. Okay, here's what that looks like. I'll go over the segment tree first. So you have a segment tree, stores leftmost, rightmost, what it needs to propagate, the min value, normal constructor, recalculate just recalculates the min value. To propagate, we push stuff to the left child and the right child, and then call recalc. To range add, we return if the range we're adding to is outside the range this node is responsible for. If the range we're adding to covers what this node's responsible for, we add to our propagation value, and then we add to the left and right kid, and then the min is just the min plus the propagation value. Okay, for the segments, we want to sort them by cost. That's the only special part here, so we do that. And then for the actual two-pointer sweep, we have a left pointer and a right pointer, and our answer, which we print at the end. And we just say, well, the left pointer is less than the end. We look at the minimum thing in the segment tree, and this will tell us whether we can reach all the way across or not. If we can't, we need to continue reaching across by continuing to add more segments. Okay, yeah, so that's the solution to problem E. Cool. Yeah, pretty easy, I thought, if you're familiar with that sort of thing. Good graph, I thought was a great problem. However, getting Java'd over here. I'm pretty sure, anyway. It's possible there's a bug in my link cut tree, and it has really good data, but I'm pretty confident it's just silly Java stuff. So, yeah, I'll talk about the solution to the problem. I won't go over my code because it's in Java, so it means nothing anyway. It's going to be too slow. But yeah, the idea behind the problem is you have some graph, and you're going to consider adding a bunch of edges to the graph. So maybe you consider adding this edge that has weight 1, then this edge which has weight 0, and then maybe you add this edge of weight 0, you add this edge of weight 1, and now you're considering adding this edge here. So maybe the edge you want to add is of weight 0. The edge is considered bad if after you add it, there's some cycle which has an XOR of 0 across the cycle. In this case, if you look at this cycle here, this has an XOR of 0. We have a 1 here and a 1 here, and 1 XOR 1 is 0, and that's the only things that aren't 0 in the cycle. So we have an even number of 1s. This is bad, it doesn't work. And alternatively, the interesting part here is that whether this is 1 or 0, let's say this is a 1, if it's a 1, we also have a problem, because now although this cycle is okay, we have this cycle here, which has 2 1s now. So that's a problem. Yeah, it doesn't work. And it turns out that anything of this shape, anything where we have an edge that's part of multiple cycles, is not, it's going to have one of the cycles that it's part of is going to be odd, right? Or maybe not one of the cycles it's part of, but one of the cycles in the graph is going to be even, excuse me. It's going to have an even number of 1s. There's a nice proof for that, which looks like this. So you've got this edge. It's part of 2 cycles. One cycle like this, maybe. One cycle, maybe the cycle looks like this. So maybe there's this shared part here. So if this edge, whether it's, let's say this edge is, let's say it's even. You've got this part here. This has got to be odd, right? Let's say this part's odd, because this part's shared. So I guess you could have this part's odd here. But if you have this part which is odd, that means this part needs to be even, and this part needs to be even, which means you have a problem. This cycle here is even. So if these two are both odd, the outer one is even. And if this outer one is odd, what that means is, well, the other one's odd, right? So that means that if you look at these two inner cycles, they both use this the same number of times, which means the parity of this part and the parity of this part have to be different because the cycle is odd, right? So if you add two numbers up and it's odd, that means their sums have to be different. So since these two parities are different, that means if the outside one is odd, that means one of these loops is going to be even and one of them will be odd. Okay, so there's the proof that the thing, it can't have any edge that's part of two cycles. So you can't ever have something that looks like that. Yeah, okay, so what does that tell us? That means it's a cactus. We have a cactus. Hooray for cacti. Cacti is just a graph where no edge is part of multiple cycles. Or it can be part of one, but not part of any more than one. Cool. So now, how do we solve the problem? Well, let's say we're considering adding an edge. There are a couple of reasons the edge might be illegal. One reason it might be illegal is if on the path, or let's say there are multiple paths. So if we already have two paths here, right? So maybe we have some path this way and some path this way. We just proved if there are multiple paths, we can't add this edge. Okay, so that's one reason it might be illegal. There are other reasons it might be illegal too, though. If this is a 1, and these two are both like if these are 1, and these are already connected, right? There's some path, but the path is odd. That means this is illegal, but for a different reason. So in this case, yeah, in this case, it's also bad, but this is kind of different, right? It would still be a cactus even if we added this edge. However, the cactus would have an even cycle, which we can't have. So those are the two cases. Either it would make it not a cactus, or it's still going to be a cactus, but it's going to be a cactus with an even cycle, which we don't want, so we shouldn't add the edge. So we need some way of handling those two cases. We can do this using a link cut tree. So there are some operations we need to support. We need to support like range mark all edges. And then we needed to support range sum. So what we can do is if we imagine we have some tree, right? Let's say the tree looks like this. This is some path in the tree. Maybe we have some other stuff going on. If we want to consider adding this cycle here, what we need is for this path in the tree, we need to know what is the sum of its edges. Are the edges in this tree, do they sum to an odd number or an even number? And then depending on whether we're adding an odd or an even number, that's what we're looking for. Okay, so we have that. We also want, are any of the edges here part of a cactus? So it's possible that we have, we already added this edge here. In this case, although we only have one path between these two nodes on the tree, we also have this white path here. So there are multiple paths between these two, which means we can't add this edge because it'll destroy the fact that this is a cactus. We can know that by every time we see an edge that we add, we mark all of the edges along the path as part of a cycle. So now, to see if this would break our cactus, we just need to say, in this path query, are there any edges along the path that are already part of a cycle? And this is, again, just a range. It's like just a path on a tree query, so we can do it with a link cut tree. So we do both of those, and then if we're going to add this edge, then like in this case we wouldn't, but in this case we would because no nodes are marked. Then we have to mark each of these nodes as these are now part of a cycle. And we don't actually, obviously we don't add this to the link cut tree because it would be no longer a tree, but we know that each of these nodes are part of their one and only cycle, and no edges ever get deleted, so we don't need to handle that. So we should be good there. Okay, yeah. I thought it was a great problem. I really enjoyed the problem. However, the time limit is too tight. It's obnoxious. So yeah, I was kind of raging about that contest. Yeah, so that's educational round 112, along with, I think, all of the solutions. The runtime for this would be n log n, which should be fast enough. I mean, there's a little bit of overhead because it's link cut trees, so it's a little bit slower than that, but I really feel like that's a correct solution. Even if it's not intended, it seems like it should be a correct solution. So, yeah, should be fine there. Anyway, okay, that's my contest. Those are my solutions. Hope you enjoyed, and hopefully they help you understand something, if that's why you were here. Have a great day, and I'll see you in the next contest.